All right, thanks, Anka.
Let's try to hear Vincent. Welcome, Vincent.
All right, so I'm going to be talking about simulated perception. So the context here is that we've been working on grasping from visual input for some time now. So the setting is you have an arm that's trying to pick things up from a bin, and we can learn that entire grasping behavior just from vision input. And the catch is that it takes about 1 million grasp attempts to get to a good performance in that setting. And so that means a lot of hours of training data. And we can parallelize on multiple robots. We have a little arm farm that enables us to do that, and that's nice. But that's not very scalable. And the question is, how do we do better than that, right? How do we improve on that? So we could scale up by just throwing robots at the problem. But Uncle Google would rather if I spent more energy trying to scale up on all the computers that we have out there. And so the question comes, can we do a lot of this in simulation as opposed to on real robots? And simulations are kind of attractive, right? We could potentially simulate on tens of thousands of cores. And then, of course, we have the problem of transfer, especially for perception. That's a huge problem. The models might not work well in the real world if we just do the naive thing of training on simulation and testing in the real world. So how do we bridge this gap, right? How do we actually make sure that what we get in simulation can actually transfer into behaviors that work well in the real world? So I'm going to give you two perspectives on the problem. The first one is we have all those nice models that have been trained on real data, lots of real data on ImageNet or on MS-COCO and things like this. Can we use those as primitives in simulation, learn things in simulation using those models, and then transfer that back to the real world? So that's the first question. And the other question is, can we bridge the gap between simulation and reality using domain adaptation techniques? So first part is about object detectors. If you're familiar with the object detection literature, there is sort of a general theme around how you build an object detector today, right? You have a feature extractor of sorts. You have a proposal generator that generates boxes. And then you have a classifier that classifies those boxes into various objects. And there is a lot of variations around that theme, but they essentially all mostly look like this. And the question is, we'd like to incorporate synthetic data into our object detectors, right? We'd like to, there are a few reasons. We might want to have some strong guarantees about certain objects being recognizable and detectable for a wide variety of distribution of views that don't necessarily occur in naturally occurring images. We might want to tailor the detector to a specific task, and so do more instance detection as opposed to class detection. Or maybe we have a much more complex simulated pipeline and we just want to incorporate that detector into the whole thing. So can we just naively throw synthetic data at the problem and hope that it works? Well, not really, right? It doesn't really work. So we've tried on, here's two different cameras and two different types of models. The precision that you get if you just throw the simulated data at the problem is really terrible. But all is not hopeless, and this is a teaser of what we can achieve. Those are the objects that we've seen in the synthetic data set, and we can actually track them pretty well at a very high accuracy and very high frequency. So how do we do this? Well, the first thing is to try and do the classic sort of data set augmentation techniques, right? So we rotate, change the pauses, change the lighting, add random illumination, noise. We can blur the images, do all the traditional thing that we would do with regular images, and that helps quite a bit. Another thing that we need to look at is, well, now we are training on very specialized data that looks different from data in the real world. We basically have losses that flow through the network that try to generate good proposals, that try to classify the box classification loss as well, and all these gradients flow back. And then if we just naively train on synthetic data, we basically destroy the feature extraction part, because simulated data tends to be very specific, doesn't match the real world. So a very natural thing to do is to use a pre-trained feature extractor and just stick to that. And in fact, if you just pre-train the feature extractor and don't propagate gradients and just learn your proposal generator and your box classifier on your data, you end up doing pretty well. So those are numbers on 2 different architectures, Inception ResNet v2 and ResNet v1, on looking at synthetic data versus frozen, the frozen feature extraction, and we get pretty high accuracy, and in practice it works very well. So the idea is not very deep in itself, but it's kind of interesting that when we think about simulation, we think about throwing away all we've learned from the real world and starting from scratch and learning very complex pipelines directly from simulated data. Well, we don't have to do that. We can actually just use detectors and classifiers that are used in the real world, apply them in simulation, and if we take care of doing that right, we can actually use that and get still good performance in the real world after we've done everything. So that's nice. Let me switch on to the second topic, which is using domain adaptation. And the setting there is that we have all this domain adaptation literature that's emerging around generative adversarial networks. Right? The idea is that you have a source image and you learn a generator that maps your image to a target domain. In this case, the source image will be the simulated image. The target domain will be the real image that we will use to train our network. And then we have a task model that we want to use to train these images, to use these images on to train for a specific task. And the goal is to generate images using this generator that will be useful for that domain down the road. The key idea there is that we want to learn those transformations at the pixel level. And the nice thing about doing this transformation at the pixel level as opposed to adapting the model itself is that now the target images that we actually have a lot of freedom to use them for whatever task we want. Right? They're raw data. They're not a model that is designed for any particular task, and we can reuse them in any way we want. It's just another way of doing data augmentation. So the setup that we use is a classic sort of GAN setup where we have a generator network, discriminator network. In order to stabilize the GAN, we also use auxiliary losses like a task model that basically maps on both the source image and the target image to the task that we want to accomplish. And we have this content simulatory loss between the source and target images to make sure they're close together. The problem with GANs is that if they have a chance, they will try to cheat. So if you have an image that is, of an object in a certain position, and to map it to the other domain that you care about, to the real domain, it helps the system to actually move the object. It will do that. It will have no qualms about actually transferring the pixels from one position to the other. And so you lose the semantics that you wanted to have, and your target image might not look at all like the source image that you have. So to stabilize that, we basically need to have some content similarity loss in between the two. I already basically went through all this. So experimental evaluation, we've looked at it on a toy task just to prove that this idea has legs. So this is just transferring from MNIST to MNIST-M, which is a data set that is just MNIST with random backgrounds in the back. And we can train a model on MNIST, map the images to the target domain, and actually get perfect results, or almost perfect results. So the idea is not a bad idea. In practice, when we want to apply that to the more concrete task of grasping, where the images are a lot more complicated. Right? So we have a measure of success, which is whether we actually manage to pick an object from the bin, and it takes a while to train. So we've developed a variant of this pixel domain adaptation model, which is dedicated to the task of grasping. We combine both the pixel level domain adaptation with some feature level domain adaptation in the pipeline. We train it on a lot of simulated data. One of the interesting features of that work is that the objects that we use in simulation are actually completely random. We didn't have to generate new content for this. And we can apply it on real objects in the real world, but we can train on just randomly generated objects. So if you compare the chart on the right there, this is looking at, on the x-axis, the number of real-world samples that we need to use during training. The red curve is what we get if we only use real objects, so we get pretty good performance with about 1 million samples, and we saturate around 10 million samples. We can't really improve much on this. If we add simulated data to it, we can actually get pretty high performance pretty quickly. So even with 200K samples of real data, we get very high accuracy. But what's more interesting is that we can actually improve on the best performance that we've had on even using all the real data that we have, which seem to have saturated in terms of performance, but adding those simulated examples actually helps quite a bit on top of that. So that's very good news. That means we're not just improving efficiency of training, we're actually improving accuracy as well. So that's a good feature to have. The dedicated model uses semantic loss as the auxiliary loss. So as I mentioned before, having a content-aware loss helps making sure the semantics are preserved between the images that are simulated and the real images. Semantic segmentations make sure that the things remain in place through the transformations. All right, so conclusions. Two things of note. It's okay to use simulations. You can still use your pre-trained model, your favorite pre-trained models. If you freeze the feature extraction, things are going to be mostly fine. And then domain adaptation actually works, and we can actually map simulations to reality without a single real-world label, and that's very important. We can actually just train on purely simulated data. As long as we have a corpus of real images that we can draw from to train our GAN, we're actually doing fine. And that's it. I had a quick plug here for Quarrel, which happened this past week, and will be in Switzerland next year. So keep an eye out for the conference next year.
Yes, please submit to Coral. Thank you, Vincent. Next up, we have Sergey Levin from UC Berkeley.
All right, my name is Sergey Levin, and today I'm going to talk about imitation from observation. But before I do that, let me set up a little bit of background. So, as I'm sure all of you have seen before, in recent years, we've seen a lot of big successes from machine learning, in particular deep learning techniques, for handling highly unstructured real-world environments. For example, we've seen that we can do a good job of detecting various categories in images, translating text, recognizing speech, and so on. But what about learning behavioral skills? What are some of the considerations that we need to keep in mind when it comes to using deep learning techniques and extending them to robotic domains like robotic manipulation or mobility? Well, in my group, we've been working on this for some time. We had some results a few years back on using deep learning to learn a variety of manipulation skills, which worked well in some situations. They even generalized to a variety of different situations. But with pretty much every skill that we were able to get our robots to learn, there were always some situations in which it didn't do so well. So here, this robot learned to put caps on bottles, but if I was holding the bottle and my shirt is a similar color to the robot's arm, then it doesn't do such a good job. It actually misses, it gets confused. Now, a few years passed, we've done a better job of it. Now we can have a robot that can pour some almonds into a cup. Sometimes it spills a little bit, but generally does a very good job in a variety of different situations. The range of situations has increased, but there are still a few cases where it doesn't do so well. And this might get you thinking that, well, okay, we can keep improving the algorithms, we can give them more data, we can train them for longer, and they'll keep getting better and better. But I think in the end, it's going to be very difficult for us to ever build a system that never ever makes mistakes. In fact, there isn't even an example in nature of a creature that is so smart that it never makes mistakes. So perhaps what we should do instead is think about how we can build systems that make mistakes, but then learn from those mistakes and get better and better. So over the past year or so, we've been doing quite a bit of work in my group and also with collaborators, trying to develop systems that can continue to collect their own experience and get better and better in various ways. So this slide just shows a few of the works that I won't cover in detail in today's talk that get at some aspects of this. In the top left is a project on learning predictive models from experience. You can see in the middle some projects on mobility and so forth. Let me go through a few ingredients that I think are really important to have if you want to build robots that can continue to get better and better through their own experience. One of the ingredients that I think we ought to have is the ability for the system to collect its own data, specifically without the need for extensive human intervention. And we've done some work on this. So here I'm showing two projects, one on grasping, where the robot grasps objects using a touch sensor and collects its own experience, collects its own labels, and the other one on mobility, where this mobile robot drives around, collides with things, and learns how to avoid collisions entirely through self-supervision. Another thing that we'd like to be able to do, if we want robots to continuously improve and fix their mistakes, is to be able to reuse their experience for various tasks. So we don't want a machine that just does one thing. We'd like to have a large repertoire of behaviors, and that means that we need to use the experience we've collected to become better at all the things that we'd like to do. So this might involve, for example, learning a predictive model of the world. So this is a project where a robot actually plays with objects on a table, learns to predict future visual observations, and can then use those predictive models to perform tasks. So that's important also. We'd like to be able to adapt quickly. So we don't have to, so that we don't have to make the same mistake many, many times before we figure out what's going on. And we've been exploring meta-learning techniques, techniques where the robot can actually learn to learn more quickly through its experience and through data, and I'll talk about those a little bit. But the topic that I'll mainly focus on in this talk is how to automatically evaluate goals. And I think this is a somewhat underappreciated factor of continuous robot learning, which is that it's not enough for the robot to just do things in the world. It needs to understand whether it's doing things that are actually productive for any particular end goal that it might consider. So there are many things that it can go out and do that are completely useless, that lead to no useful end, and it needs to understand what kinds of things are useful, what kind of things it might be asked to do at test time. So we need some way to automatically evaluate goals, and this is actually surprisingly difficult. Oftentimes when we think about learning behavioral skills, we think about frameworks like reinforcement learning that basically assume that the objective for the system is given to it, that it's a, sort of an external part of the world and it's provided to you free of charge. So if you're learning to play a video game, for example, there's a score to that video game, and that's the thing that you have to pay attention to, and you don't have to worry about where it comes from. But in the real world, if you have, let's say, a household robot and has to do a variety of chores, maybe you can leave it alone in your house and it will practice various things, but it needs to know what kind of things are actually useful to do in a house. So if this robot is sweeping up some crumpled piece of paper, well, it needs to understand what success actually looks like, and it needs to be able to evaluate that using its own sensors. So how can we acquire these large repertoires of objectives, which are a prerequisite for then acquiring large repertoires of behavioral skills? I would argue that one very good way to acquire these objectives is to observe people. But if we're going to acquire objectives by observing people, we need to be able to use data of people that is freely available to us, that is something we can obtain very easily. And that basically means things like videos. So what I'm going to discuss is a number of projects that get at this idea of how robots can learn behavioral skills just by observing people doing them. So that maybe in the end you might imagine a robot goes on the internet, types in a particular thing into YouTube, how do I build a deck in this case, gets a video, analyzes that video, and figures out how to do things. Now, we're not anywhere near there yet, but I'll talk about a few initial steps that we've taken in that direction. So the first project I'll discuss is called Imitation from Observation. This is by Abhishek Gupta and Andrew Liu. And the idea here was to take kind of a first stab at an end-to-end system for learning from videos of humans. And the way that we did this here is by assuming that we get demonstrations of a particular skill in various contexts. So a context can be something like a different viewpoint, or a different background, or a different pattern of distractors. So it's the same behavior illustrated in each context, but there's some kind of variability. And if you get a variety of demonstrations from different contexts, What you can learn to do is translate from one context to another. That means that you take an entire video of the behavior in one context and the first frame of the video in a new context and try to generate all the other frames in the new context. So it's a kind of a translation model. So let me show an example here. These are two demonstrations provided from different contexts. In this case, the context is just viewpoint. In both cases, the demonstrator here uses this brush to sweep up some dirt, but the viewpoint is different. And we can collect maybe 100 of these demonstrations, learn to translate from one to another, and then when the robot sees this scene holding the same kind of brush from maybe a new context, it can translate one of the demonstrations into its own context and then use reinforcement learning to learn to track it. So the features inside the model for that predicted sequence actually end up being the reward function. And then you can see here the robot is actually, after using reinforcement learning to learn to track a translated demonstration, it can figure out how to sweep up this dirt. And this is done entirely from raw images. So all the robot gets to see of the world, other than its own proprioception, is the pixels in the image. Here's another task, and here I'm going to actually show the translations to give you a little bit more intuition of what's going on. So in this task, the human demonstrator uses a spoon to show the robot that he wants some nuts to be scooped into a pan to make a delicious dinner. And there are 60 of these demonstrations in different viewpoints. The model gets an input at a slightly lower resolution, so this is what the model actually sees. And then now it's going to try to translate another demonstration into a new viewpoint. And the translation is kind of blurry, it's not great, but remember that what we really want is the underlying visual features. So we're going to pull out those visual features, give them to the robot, and it will attempt to do the task. And it's not perfect, it spills a little bit, but on the whole it actually gets the majority of the nuts into the pan entirely from raw image observations. And the bottom row there is showing some previous methods. Okay, there are a few shortcomings to this method. One of them is that it requires quite a large number of demonstrations. And the other one, which some of you might have noticed, is that in all these tasks, the human was actually using a tool to demonstrate the skill. And that's because a human's hand looks very different from the robot's hand. So there's a systematic domain shift. So we decided not to handle that in that project and just use tools. We can actually address both of these issues by using a meta-learning approach. So in this next project I'll discuss, we can actually get a robot to learn from a single demonstration by assuming that at meta training time we have a variety of different tasks, other than the one that we'll want to do in the end, that each have a training demonstration and a validation demonstration. And the way that the system is going to work is that the robot will observe the training demonstration, and then it will be asked to do well on the corresponding validation demonstration at meta training time. So that at meta test time, they can just get a single demonstration and generalize from that to the new desired skill. So here's an illustration of this. First, I'll show what happens with teleoperation, and then I'll talk about demonstrations with human videos. So in the teleoperated case, this is meta test time now. The human teleoperates the robot to drop the sapple onto the plate. The robot uses the model that is meta-trained on all these other tasks to figure out how to generalize, and then you can go in and rearrange the objects and can figure out that in fact it's the blue bowl that matters. And this is actually the first time that the robot has seen the blue bowl and the yellow plate and so on. So these are new objects that were not there at meta training time. Now this is not from a demonstration of a human. If you have a demonstration of a human, you can actually do it also, and I'll say in a minute how this is done. So first, the way it looks, the demonstration, the human shows with his own hand that he wants to drop the peach onto the plate. The robot observes that demonstration and then tries to do it itself. So very quickly, the central idea behind this algorithm, this is based on something called model-agnostic meta-learning, is that the model is going to be adapted at meta-test time by taking a gradient step on the objective to match the demonstration, and at meta-training time, it's actually trained so that that one gradient step does as well as possible in the corresponding validation demonstration. Of course, if we have a demonstration of a human, we don't see the ground truth actions, so we can't actually figure out what the supervision is. So the way that we solve that is by actually learning a loss function during meta-training time that can process raw human videos and then do well in the corresponding validation demonstration. So if you want to learn more about this, please come talk to me after the talk. And I'll wrap up right now. So I talked about how we can autonomously evaluate goals, and these are the collaborators for this work. Thank you very much.
Thank you, Sergey. Next up, we have Jitendra Malik, also from UC Berkeley.
Where's the... Oh, okay. No, this won't work for me. I think. Oh, yeah, I see. Yeah. Thank you. Yeah, I'm just being dumb. Hello. Okay, so I'm a computer vision guy. I've been working on computer vision for many years, 30 years, more than 30 years. In the old days, vision labs and robotics labs were always the same lab. And things changed in the 90s. I think in the 90s, the vision people abandoned robotics, and the robotics people abandoned vision. And the vision people went off to graphics and then to learning. Those were the cool kids. Robotics people were like, I don't know. And I think the robotics people started to ignore us for a very good reason. They would come to us and they wanted something very specific done. Can you recognize this widget? And we would give them hem and haw and have sort of long stories, and we couldn't exactly deliver, so they went off and ignored us. So there was all this work which was trying to ignore sensing. Now this is very silly, right? Because if you think about intelligence, it has always been about perception together with action. You cannot have robotics without perception being half the story. Now, so this is kind of a story that we all know about, and I think at this point now vision works. So I think it's time for vision people to get into robotics and for robotics people to pay us very, very good attention. Okay. I want to start with this story because this is the philosophy which drives my work these days. Look at children. I mean, these are the best learning machines, the best robotic machines, the best vision machines that we know of. And what these kids are they are experimenting, they're doing sensory motor calibration. They are like the scientist in the crib. So when they poke around, there you see the hand, they see the eyes see the hand, there is the proprioceptive information, all of this together. That's how infants learn. Now, if you look at the top, that's this model where the mother says to the child, look, that's a zebra. Okay, now imagine that the mother says for another image, this is a zebra, and this is a zebra, and this is a zebra 1,000 times. Well, that's the way we do things these days. That's supervised learning ad nauseum. Okay, this is not what happens for children, right? The child who comes into the zoo is already a visual genius because he or she has played around with the world and has the sensory motor system to which one example of a zebra is enough. So this is what we want to do. So the whole story is, I am interested in building up a sort of vision, robotics, etc., from this axiomatic baby development setup. Build in minimal stuff, and then after that, have a series of experiences through which the child will learn, or the robot will learn. There is a lot which is known from the cognitive development literature. It's been going on since Piaget in the early part of the 20th century. But there's a big literature. I'll give you one reference if you want to chase up on something to read. And there are a series of lessons, multimodality, incremental, embodiment, combination of exploration and exploitation, be social, use language. Obviously, from us as computer scientists or machine learning people, we have to find a way to computationally operationalize these ideas. And that enterprise will take some time. But to me, this is the right journey to be on, okay? So I'll give you two examples. So think of these as case studies. Okay, so the first one is work which is sort of a manipulation. Let me see if I can get this thing to, okay, so this is learning to poke by poking. This was a paper last year at NIPS. So you are doing, so this should remind you of that baby flailing about, reaching out to objects. Now, in this case, no external annotation has to be needed. You don't have these armies of AMT workers marking objects. You just have a series of these experiments. And from these experiments, what do we know? We know before and after. So there is an initial configuration. There's an image taken of that. Since the robot performs the action, the robot performs a poke, so that is known, right? So this is what neuroscientists call the efference copy. You know what you commanded. And then there is the resulting configuration. So that's the triplet that we have. And what we want to do is to understand this triplet in some way, which means that now we don't want to predict pixels. So what we can do is we can imagine we run it through a Siamese network, and you try to predict the poke, which you know in advance because you commanded it. So that gives you a loss function that you can use for training this network. A key insight here is that we should train two models, an inverse model and a forward model at the same time. The forward model, if you will, is simulation of physics. If there was this Coke bottle and you poked it, it will fall down, right? That's physics. That's forward model. And children acquire intuitive physics through their experiments in the crib. The top part is the inverse model, which is the other way around. I have an initial configuration, a final configuration. What should I do? What's the poke? That's the planning model that tells you what to do so as to achieve the desired result. And you can train these guys together because they're roughly like F and F inverse, and they will stabilize each other's training. Okay, not to go into more details, but these are demos. And the point is that there's considerable generalization. You can generalize over multiple objects. It can generalize over the fact that you need to do multiple steps while the training is done for a single step, et cetera, et cetera. And we are now building on more things related to this, which is, can we acquire the notion of an object through these experiments? And I won't get into details on that. And of course, this area is being pursued by many labs, and I think this is very worthwhile. Then, when I was a student at Stanford, I learned this line from Don Knuth. If something works once, it's a hack. If it works twice, it's a technique. So therefore, we needed to have one more example, okay? So this is on rope. I think that in one of the short talks today morning, Pulkit Agrawal showed this demo where there's this rope where the human specifies what the final configuration is, and the system learns, and it's based on sort of a generalization of the ideas in the previous work. Okay, so since it's worked twice, it's a respectable technique. Okay, then I'll give you another example, which is now in the navigation domain. So manipulation and navigation. I think, let me describe the setup. We have a robot, we have some environments. This was a beautiful case where the whole research was done in a synthetic environment. Well, it was not a synthetic environment. These are environments of some buildings at Stanford. So they're simulations derived from captured reality. And, but then we actually tried it at Berkeley. Now, one would think that something which works at Stanford will not work at Berkeley, because we all know that Stanford is clean, safe, and boring. Berkeley is the opposite. Okay, and I think the demos actually show that. I didn't intend it to show that, but it does show that. Okay, well, what's the point? Let me get back to serious stuff. So classically, this is like 20 years of work. Okay, in computer vision, we call this structure from motion. The robotics people renamed it to SLAM. Fine, okay. You can call it what you like. We call it structure from motion. So the whole idea is you first build a detailed model of the world in its excruciating detail. Every damn thing in the world has to be modeled. Okay, then you convert. Now we've got a problem which is now a computational geometry problem, plan a path. This does too much and it does too little. We don't need a map of every damn chair in this room in order to find a way to get out of the room. That should not be necessary. And yet it does too little, because this model doesn't know that if I open that door, there's going to be very likely a corridor. Because all the model sees is the detailed model that it has built up of the geometry in the world. And there's no semantics in there, et cetera, et cetera. So we want to take this classical design, but convert it into an architecture which can be trained end to end. And that's what we did. And again, there's a poster on that still there. Saurabh was presenting it in the morning and afternoon. So the basic setup is we have these images which are being sucked in, used to build like a bird's eye view of the environment, and then doing planning in that environment, so which is essentially value iteration to determine what places are closer to the goal in some sense. And you take an action, and then you replan, et cetera, et cetera. The beauty of this is that you can train in some environments and get experience of those environments, so that doors open into corridors, et cetera, et cetera. And then you can go into a new environment and then rerun this, and it's going to build a map and plan. And the examples that are nice are, So for example, here you can see that as the robot moves around, its experience is reflected in the free space maps that you see here. And then here are some runs of the robot in simulation. These include, by this memory of building up this map, it can in fact do backtracking, etc. We have these experiments which show that this architecture does much better than a simple LSTM kind of baseline, which is one way to build in memory. So this architecture based on previous designs from the robotics community was actually helpful. We just had to make a differential end-to-end training setup. Some more details, and then I'm concluding here with these pictures of real-world demos. Thank you very much.
Thanks, Jitendra. Next up is Alison Okamura from Stanford.
Okay, thank you very much. I'm Alison Okamura from Stanford University. Thanks to the organizers and local hosts. I'm going to talk today about Vine robots, which do mobility and construction by growth. And I should definitely credit the folks behind this work, my former postdoc, Elliot Hawks, who's now an assistant professor at UC Santa Barbara, my current graduate students, Laura and Joey as well, who are here today. And you saw Laura's earlier teaser and poster on building antenna out of these types of Vine robots. So a little history about how this came about. About 2 years ago at BARS, I spoke about our steerable needles, medical robots that could curve through soft tissues to get deep in the body in the most minimally invasive fashion possible. And this idea was great, except that we do have friction with respect to the environment, and that can make it difficult to steer. In addition, we had parallel work in our lab, which I talked about last year at BARS, on soft haptic devices, using soft robotic techniques to get objects to change their shape and mechanical properties. And this inspired us to think about new actuators that could be soft, yet change their length in order to control these devices. And so putting these ideas together, thinking about steerable needles and soft robotics and soft haptics, we started working on this concept of pneumatic growing robots, which embody some of the important concepts that we're looking for. This includes being able to lengthen a robot from the tip rather than sliding the whole thing, making sure that with respect to the environment, you remain static so that you can get easy access through difficult to reach places. And then finally, following a kind of follow the leader approach where you keep growing out of the tip and that lets you be mobile and push off of yourself rather than the environment. So this concept of a growing robot, of course, has some analogies in nature. There are pollen tubes and there are nerve cells that grow. We're interested in things that are more on the human scale, and so we look to plants, in which case, if you're a gardener, you're probably the bane of your existence are vines, plants that have this growth habit of trailing, where they keep extending their length, they can stick to the environment, and they can get places that animals and even other plants can't go. And so this image at the bottom here shows our Vine robot having grown and stuck to the side of a building and then slipped through the crack in a door. Now, there are other researchers who have thought about plants, of course, as an inspiration for robotics, and we're trying to push the envelope in terms of the speed and mobility and steering of these kinds of technologies. The basic underlying mechanism is as follows. You take a thin-walled plastic tube, kind of the consistency of a Ziploc bag, you invert it, and you feed more material out through the tip. And so if you pressurize it, it will grow. In this case, it's pressurized with air. You could also use other fluids. And then if you pull back on the material that was fed through the tip, then you can reverse the process. If you're having trouble picturing what this is like, you might have played with one of these water snake toys. My kids love them. And they're very slippery because they easily move through their interior structure, but then don't have to slide with respect to the environment. There are some other concepts, again, in robotics that are able to achieve this kind of behavior. What we want to do is make these a robot by actually being able to control and steer this behavior. So how do we construct this into a robot? Well, for starters, we need to have a mechanism that allows us to grow. And so to do this, the diagram shows how we have a spool of this material inside of a pressurized chamber. We sort of pull out the end of the tube and invert it and then apply more pressure. That will cause it to grow. And you can have a motor at the center of the spool if you want in order to control how fast it grows or even make it stop growing regardless of the air pressure. The video at top right shows how such a device can actually grow upwards and for a pretty good distance, on the order of 5 to 10 meters, actually support its own weight, and then eventually, if it gets off center, it will buckle and fall over. But that's all without being supported, and so you can imagine you start creating sticky points that grab onto the wall at different locations, then you can actually go straight upwards, which is really difficult to do with other types of snake-like type robots. The last two videos, which I'll play in sync at the bottom, even though they're not actually videos in sync, show one video close-up of one of the spools unfurling in a chamber that's about this big, and the other is a video of a previously grown Vine robot. And I'm going to put robot in quotes here because this one was not smart, it didn't steer, it didn't have any sensing, but it has the kind of embodied intelligence that we use soft robots for, which is that it bounces off the environment, kind of makes its way to some location. At this point, we aren't controlling it yet, but you can see that it starts, especially here in the video, you can see it kind of gets behind those pipes, and it's able to keep going. And I love the end of this video because it goes all the way, the video goes to the base, and then you see all the grad students' feet standing around watching the robot. Eventually, it will get there. There we go, all the grad students' feet. So that showed the base, and so you can see it's pretty compact. So of course, to make this a robot now, we want to actively control it, and that means steering it. And so we want to simultaneously grow it and change its direction. And there are many different ways to do this, and I'm going to give two examples, one which is a permanent direction change, and one which is reversible. I think ideally we would like reversible direction change, but you can make the permanent direction change a little simpler in terms of the actuation technology. So the videos that are playing right now, the basic concept is in order to make it turn, you pinch the plastic and you tape it, essentially, so that if you have a pinch, it's going to make a curve when it grows. And you can do this in advance. I call it mechanical pre-programming of the robot. But basically, it's a grad student with tape. And when you do that, if you have planned in advance, you can have this pre-programming, but let's say that you didn't really know exactly what the environment was in advance. And so the bottom video shows a video taken from the top, which is finding obstacles, and what we're doing is we are holding the robot back with a string through the middle, increasing the pressure when needed to pop open these pre-taped bends. And so as the material emerges from the tip, we can, in real time, at the time that we need to, not allow a turn instead of using the pre-programmed turn. So it's kind of counterintuitive. We're kind of unpinching instead of pinching as we grow. And that's just one way to do it. For reversible, again, we have different techniques, but I'll give one example. This is from an ICRA paper we presented last year, where we use a kind of pouch motor approach. Basically, we use another plastic tube, thin-walled. We pinch it together in different locations, and when you pressurize it with air, the little pinched portions go outwards and therefore shorten the length. And so you can create a bunch of kind of pneumatic tendons out of this and put them around the outside of your growing robot, and then you can use this to turn left, turn right, and then move forward rather than being forced to grow in order to turn. So in the bottom video, we show this actually being used in real-time control with a camera at the tip, and I'll use the videos on the next slide to talk about how that works. So in these two cases, we have a camera sitting on a platform that's at the tip, and we're tensioning that platform through the middle of the robot with a string. And so as the robot grows, it pushes the camera out in front, and we can pull back on the camera to sort of prevent it from falling out altogether. Although you can see in some cases it does kind of ahead of itself. And so here we're actually doing real-time control in order to look for a target. You can actually see the visual feedback in the top right of the left video. We're growing towards the light, we're changing the direction, and controlling growth all at the same time. So these are actually completely autonomous behaviors to get to particular targets through both growth and steering. Now, this is a nice, sophisticated robotic system now because it has perception and it's doing control on that. But I want to step back and just ask how much of this steering capability and perception do we actually need? And I actually love that Jitendra showed a image that looks almost just like this in his piano planning example of the classical planning problem, because what we have here is a physical version of such an obstacle course. And in this case, again, I wouldn't maybe call this exactly a robot. We're just inflating the growing vine robot, and it is just bouncing off the obstacles and using its embodied intelligence that soft robotics have in order to weave its way through and exit this different places in this obstacle course at different locations. And this is not yet planning. This is purely having a kinematic model for how the Vine robot will traverse through this obstacle course and showing that slight differences in initial angle will actually let you pop out in all kinds of different locations. And what this is showing us is that without any steering actuation at all, we can actually go a lot of places by harnessing this physical interaction with the environment. So that means when we add some steering, maybe we could add very minimal steering in order to get where we really need to go and take advantage of interactions with the environment in order to do a good job. So the next couple slides, sorry, this is a very eye-candy talk, so mostly videos. I guarantee there are models and lots of control work behind all of this, and you'll have to look at the papers if you want to know about those. But what the videos can show are some cool applications of what we can do with this robot. It can go over water. Laura talked about how it can be used to construct an antenna. We can have it squeeze through very small areas as long as it's not blocking something at the tip. So you can squish down, maybe even more than a cockroach. And then you can also get through environments like the sticky fly paper. You can go through fluid, even sticky fluid like the glue. It's about to show at the bottom. And you can also grow through nails that puncture it. And even if you puncture this, you could think relatively weak material, the punctures actually fill the holes that they create because there's no sliding with respect to that environment. And so you can see now through this whole obstacle course, it can go through all of these environments and then even slide up. We decided to create a wall of ice for some reason, I guess because it's hard to stick to. And then at the very end, you can even deliver a sensor through the middle of the device. And then the last set of application examples get to our interest in doing inspection and search and rescue applications with these devices. So the top one here shows an idea where maybe in a nuclear power plant or something like that, you have a valve which has become loose and now you've got poisonous gases coming out of it. And so if you don't want to send a human in to take care of this, could we send one of these Vine robots under a door? This one is mechanically pre-programmed, but it could be controlled in order to get to the valve, hook around it, and then while these robots are not strong in bending, they are strong in tension, so you can pull from the base, and then you can do some simple manipulation tasks at the remote end effector. You can also go through the ceiling in our lab with a camera if you want to check out places we don't normally go. And then the last example is one of my favorites. It grows over a fire and with both water and air inside of the tube. When the fire melts the plastic, it comes out and actually puts the fire out. So we have our little firefighting robot there. So in conclusion, I want to especially thank Laura and Joey and Elliot for their excellent work on this and all the new students that are continuing this work. And thanks for your attention.
Thanks, Allison. Next up, we have Hannah Stewart from UC Berkeley.
All right. Hello, everyone. It's a great pleasure to be here. I'm representing both Stanford and Cal today. I'm presenting work designing robust robotic hands for remote ocean exploration. And this is based on my thesis work under the guidance of Dr. Mark Kokoski, who spoke earlier today. But I'm starting a new faculty position at Berkeley in January. So as I'm talking, please keep in mind that I'm going to be looking for new, excited collaborators to create new projects. Over 70% of the Earth's surface is covered in oceans, but NOAA estimates that we've only actually explored about 5%. And that's because it's really hard and it's dangerous and it's expensive. So this means that robots really have a great opportunity to revolutionize the ways that we interact with our oceans. This is the platform that inspired my work. It's called Ocean One, and you've probably heard about it at bars before. Unfortunately, Osama Khatib is not here today. But the key idea is that this platform is very intuitive to use and it acts like an avatar. Now the operator, who could even be a novice user, is feeling that the forces that the robot is feeling. And this is footage from its maiden mission to the La Lune shipwreck off the coast of Toulon, France, at a depth of 91 meters. And this was a really exciting mission for us because we were able to actually acquire an artifact and bring it back. But this video masks some of the realities that we faced bringing a robotic system into an unstructured world. For example, there were really strong water currents that pushed the body into surrounding structures, and we had to improvise and use our hands and our arms to push ourselves free. So this gets at a key point, I believe, in robotics, where you need platforms that are not only highly capable, but extremely robust. Because if these hands fail at depth, it compromises the feasibility of using this platform in the field. So because of these constraints, we ended up with an under-actuated design. As you can see, there's a single input shaft and 3 fingers per hand. And what we need this hand to be able to do at a bare minimum is to be able to handle tools and structures with strength, so an interlaced wrap grasp, as well as pinch objects that are either too large or too small for our fingers to wrap around. But there are a couple considerations and design challenges that emerge when you choose an under-actuated design. And in particular, the performance of your hand is highly dependent upon the compliance in the system and your contact conditions. And usually you need to choose these things in the design process. You can't necessarily change all of them during operation. So these hands tend to be somewhat inflexible when faced with new and unexpected challenges. And while you can think of this as primarily a limitation, it's also a great opportunity. Because these hands are sensitive to these things, if we can change them in meaningful ways, even with simple mechanisms, we now have a great opportunity to make these hands address very different sorts of tasks. And while I could talk about the compliant design of these hands, I'm going to encourage you to look up the paper that we have out in IJRR, and I'm going to totally skip over that. But it's interesting, so look it up. Instead, I'm going to talk about contact conditions. How do we control contact conditions in this environment? So this is the vase that we acquired from the La Lune shipwreck, and it's covered in a thick, slimy, slippery biofilm. And while this is somewhat unique to marine environments, it's also ubiquitous, so it's something we need to be able to handle. Something analogous to this in our daily lives is a bar of soap. And so we explored how we could use something like very gentle fingertip suction flow to improve picking up this object. And I think this is a relatively straightforward idea. But what we find is that we're controlling not only where contact location is likely to occur and stay on the hand, but also increasing our normal force with a light suction pressure applied at the fingertip. We also find that there's a slight increase, or sometimes a not slight increase, in your coefficient of friction as well. So there's a couple reasons why you could get some benefits. But I'm going to talk instead about dynamic acquisition, because this is maybe a little bit less intuitive in terms of the role of suction flow. So here is, again, I think an intuitive case where you have a very small Lego piece, and it's pulled into the fingertip at a location that happens to be really convenient for pinching. So now you don't need to be fishing around in this tank trying to capture this small light object. Now this is a bio-inspired idea. Suction feeding is ubiquitous among fish, but it's not really a mechanism you see as much on land. So there's something about being in a viscous, denser fluid that makes a difference here. But we want to now ask, well, what about larger and more massive objects? As a designer, I'm interested in how much suction flow do I need, and when is it just not going to make a difference? And what we're really asking is, what's the role of water drag and object inertia in terms of the influence of gentle suction flow? So let's talk about the hydrodynamics of suction. So here's a load cell reading of the force. And just to show you, we're talking about 1.2 newtons of force maximum. So this is pretty small. And the order of distances between a fingertip and a flat plate as they get closer together is 1 millimeter. Now, to model this, we figured out that we need 2 components. The first one has to do with the fact that you have flow going between 2 plates, and you have a pressure drop, and this creates a suction force. And actually assuming that it's in viscid, Bernoulli flow is a fine approximation at distances above 1 millimeter. But then as the pump gets restricted in this region here, viscous effects actually start to matter. Even though flow is going down, the velocities of the fluid is quite high. And instead of modeling the viscous nature of the flow, we assume that the pressure of the pump is being applied directly across the area of the orifice to the object. And although that's a dramatic oversimplification, if we add these two components together, it's a pretty good approximation that we can use in understanding the role in multi-finger grasping. So now, what does this mean for multi-finger grasping? Well, I like to think of a challenging situation in the ocean as trying to grasp a floating rope. So station keeping for these underwater platforms is really hard when there are strong water currents pushing on your body. But even if you get really good at reaching with accuracy, there's no guarantees that your rope isn't going to be floating in unpredictable ways. So if you get your hand located close enough, you're also going to want to grasp relatively quickly. So the dynamics of grasping are really important here. So we emulate this situation with a neutrally buoyant PVC tube, and you can see that without suction, there's no hope of grasping this object that's really far from the palm. But with suction, we are in fact able to pull it into a pinch. And we can do this over the entire workspace of the hand. The experimental results are the dots you see here. The larger dots are a 100% success. And now we can also try to simulate this. And if we do a simulation without drag, we underestimate these outer regions. And those regions are where the object has to move over a large distance and quickly in order to be captured. Well, when we add in only object drag, we're able to capture this region relatively well. And just for a reference, this is the hand, and this is the video that I showed you earlier with the PVC tube. And now that we have an understanding of what's going on in terms of the dynamics of grasping, we can add in suction flow. And in fact, we see about a 34% increase in our grasp region. And what we really want is robots that are forgiving. You know, you don't have to reach perfectly. We want them to be successful even with reasonable errors. And now we can start looking at, from a design perspective, when is suction helpful? When is it not worth adding? And so you can see that the 100-gram PVC tube is shown in blue. If we increase it by an order of magnitude, we still get a significant increase. That's 1 Newton of force at the fingertip that's increasing your grasp region by a considerable amount. But then if you go up 1 more order of magnitude, you don't see any benefit at all. And the interesting thing is that we see some non-intuitive, non-linear results when you start thinking about the design of your pump. So sometimes you can double your flow and see no improvement in your grasp region due to suction. And sometimes you can double it and see more than twice the benefit. So it really is an interesting area to look at. Now today what I've talked about is the embodied intelligence of the end effector. And in particular, with under-actuated design, you need to carefully consider how you select and actively control the compliance and contact conditions. But this naturally lends itself to start thinking about tactile sensing and understanding what's happening at your contact. And for example, monitoring your suction flow is a really natural way in this system to do tactile sensing because you know the location of your orifice. And then finally, starting to think about manipulator reflexes. For example, if you have an operator who's really overwhelmed with the situation, suction flow at your fingertip is maybe not something that they're going to intuitively think about. So you might want to automate that. But in the end, as I'm building my lab, I really want to keep coming back to this idea that all of this has to do with the embodiment. The reflexes that you want to do and the sensing you want to do will change how the hand looks and performs. And while I focus primarily on marine operation, and I think that there are a lot of really exciting ways and applications that this can move forward, I just want to point out that there are a lot of other areas that these sorts of questions are important to ask. For example, you can imagine in any of these cases that your robot will have to either submerge or get wet at some point. And with that, of course, I did not build a whole robot, and I actually see some people here who were part of that team. It was directed by Osama Khatib again, and there were just so many talented engineers and students. Funding sources, and please, if anything sparked your interest or curiosity, contact me.
All right, let me take this opportunity to tell the speakers that if you're okay with us posting your talk online, do make sure to leave us with a form, signed release form. It's going to be at the registration if you haven't actually signed it already. Please remember to do that. And in conclusion, I just want to say thank you for attending BARS. We'll send out a survey so that you can help us make it better next year. That's not right. And I just want to say again, thank you to Ron, who actually put all this together, and to our fantastic team of student volunteers who took time out of their day to help make this event run a little smoother. Thank you so much. I really appreciate it. You guys are my heroes. And with that, BARS 2017 is a wrap. We'll see you in Stanford next year.